Welcome to JB's Academy of Science. In this lesson, we are going to learn about electric dipole, electric field due to a dipole placed in an electric field, significance of electric dipoles, and problems related to electric dipoles. Electric dipole. Two equal and opposite charges separated by a small vector distance is called an electric dipole. So it is a system of two charges separated by a small distance. Here, two charges plus q and minus q, they are equal and opposite, separated by a distance 2a. 2a is a very small distance, and this distance we call vector distance. Distance is measured from minus q to plus q. Direction of this distance is taken from minus q to plus q. Now this system is called an electric dipole. The strength of a dipole is expressed by a quantity called electric dipole moment. Electric dipole moment gives the strength of the dipole, and it is measured, electric dipole moment is measured as the product of the magnitude of any of the two charges and the vector distance between them. So dipole moment is the product of the charge and the distance between the two charges. It is represented by a letter P. So P vector is equal to Q into D. Q is the charge and D is the distance between the two charges. Here in this picture, the distance is taken as 2a, so it is q into 2a. Why 2a is chosen here is for our convenience. In some situations, the distance is measured from the center of the dipole. Therefore, if you take 2a, the distance from center to any of the two charges is a. So to avoid fractions, it is generally taken as 2a. We can take d or a or any letter. Direction of electric dipole moment is minus q2 plus q. Now, electric field due to a dipole. Here we have two cases. One, electric field due to a dipole at a point lying on its axial line, lying on its axis. Second case, electric field due to the dipole at a point lying on the equatorial line. So here, first case, let us consider a point on the axis of the dipole. So look at the picture. Here we have two charges, plus q and minus q, separated by a distance 2a. O is the center of the dipole. Consider a point P at a distance r from the center of the dipole, and the point P is lying on the axis of the dipole. Now, we have to determine the resultant electric field due to this dipole at P. So to calculate the electric field at P, find the electric field due to the individual charges. Let E plus Q be the electric field due to plus Q charge at P, and E minus Q be the electric field at P due to minus Q charge. Then E plus Q is equal to 1 by 4 pi epsilon 0 Q divided by R minus A whole square, where R minus A is the distance between charge plus Q and point P. Now, E minus Q is equal to 1 by 4 pi epsilon 0 Q divided by R plus A whole square, where R plus A is the distance between minus Q charge and the point P. Now, the resultant field at P, E is equal to field due to plus Q charge and field due to minus Q charge, resultant of these two. That is E is equal to E plus Q plus E minus Q. Now what is the direction of E plus Q and E minus Q? E plus Q is away from the charge. The blue arrow indicates the direction of E plus Q. E minus Q is towards the charge. E minus Q, the blue arrow head shows the direction of the electric field, E minus Q. Now, the resultant field E is equal to 1 by 4 pi epsilon 0 Q divided by R minus A whole square plus 1 by 4 pi epsilon 0 Q divided by R plus A whole square. That is 1 by 4 pi epsilon 0 Q can be taken outside the bracket. 1 by E is equal to 1 by 4 pi epsilon 0 Q into 1 by R minus A whole square plus 1 by R plus A whole square. Simplifying this, E is equal to 1 by 4 pi epsilon 0 Q 4AR divided by R square minus A square the whole square into P cap, where P cap is the unit vector in the direction of the dipole moment. So that gives the direction of the electric field due to the dipole. Now we know that Q into 2A is dipole moment of the dipole. So Q into 4A becomes 2P. Q into 2 into 2A. Then we can write 1 by 4 pi epsilon 0 2P R divided by R square minus A square whole square into P cap. Now, if the distance R is much greater than A, then A square is negligible compared to R square. Then we can neglect A square. Then this equation is reduced to E is equal to 1 by 4 pi epsilon 0 2P divided by R cube. So this is the expression for the electric field due to a dipole at a point on its axial line. Hope it is clear to you. Now let us consider a point lying on the equatorial line. So consider again the same dipole, plus Q and minus Q, separated by a distance 2A. O is the center of the dipole, and consider the equatorial line. What is equatorial line? Equatorial line is the line passing through the center of the dipole and perpendicular to its axis. Consider a point P on the equatorial line, which is at a distance R from the center O. Now, join the point P and each charge minus Q and plus Q. Let AP and BP are the lines joining the charges and the point P. Let theta be the angle made by the line joining the point and the charge with the dipole moment, direction of the dipole moment, theta. Now, we have to find out the electric field due to the dipole at P. To find the electric field at P, first we have to calculate the electric field at P due to plus Q charge and due to minus Q charge. Separately, we have to find out. So, E plus Q is equal to 1 by 4 pi epsilon 0 Q divided by R square plus A square, where R square plus A square root is the distance between minus Q charge and P and plus Q charge and P. E minus Q is also 1 by 4 pi epsilon 0 Q divided by R square plus A square. Now, observe that magnitude of E plus Q and E minus Q are same. Magnitude is same, only the directions is different. Direction of E plus Q is away from the charge is shown in the figure. Direction of electric field due to minus Q charge is towards the charge as shown in the figure. Now, again, we can find the resultant of E plus Q and E minus Q. Consider the drawing here. If this angle PAQ is theta, again the angle between the direction of E minus Q and a parallel line to the axis is again theta. The angle between E plus Q and E minus Q is 2 theta. Therefore, a half of that, it will be theta. The red arrow vector, which is showing the resultant direction, resultant electric field direction, that is parallel to the axis of the dipole. Now, take the cos component of the electric fields E plus Q and E minus Q. Sine components will get cancelled. So cos components will be in the same direction. So resultant field is due to the cos components. E is equal to E plus Q cos theta plus E minus Q cos theta, or is equal to minus E plus Q plus E minus Q into cos theta P cap, where P cap is the unit vector in the direction of the dipole moment. Here, negative sign indicates the resultant electric field is opposite to that of the dipole moment. Dipole moment is from minus Q to plus Q. The resultant electric field direction is opposite to that. It is direction is opposite to that of the direction of the dipole moment. That is equal to minus 2 E plus Q cos theta P cap. E plus Q into E plus Q plus E minus Q is 2 E plus Q. Since their magnitudes are same, E is equal to minus 2 E plus Q cos theta P cap. Now, E is equal to, we can substitute the value of E plus Q, 1 by 4 pi epsilon 0, 2Q cos theta divided by R square plus A square P cap. Now we can find the value of cos theta and substitute in this equation. Look at this picture. Consider the triangle AOP. Then cos theta is adjacent side divided by hypotenuse. So A divided by root of R square plus A square, that is cos theta. A divided by R square plus A square whole to the power of 1 by 2. Substitute that value of cos theta in this equation. E is equal to minus 1 by 4 pi epsilon 0, 2Q A divided by R square plus A square whole to the power of 3 by 2 into P cap. Now, 2QA, it is Q into 2A. Charge into distance between the two charges is electric dipole moment of the dipole. Then, substituting the value, E is equal to minus 1 by 4 pi epsilon 0 P divided by R square plus A square whole to the power of 3 by 2. Now, for R much greater than that of A, we can neglect the value of A square, negligible. A square will be negligible compared to R square. So R square plus A square is nearly equal to R square. Then this equation is simplified to E is equal to minus 1 by 4 pi epsilon 0 P divided by R cube into P cap. Now, so earlier, in the case of electric field due to a dipole at a point on the axial line, we got the expression E is equal to 1 by 4 pi epsilon 0 2p divided by r cube. Now, if you consider a point on the equatorial line at the same distance, then electric field is 1 by 4 pi epsilon 0 p divided by r cube. So we can see that electric field at a point on the equatorial line is half of the electric field at a point on the axial line. Now let us discuss when a dipole is placed in an electric field, what would happen? So consider a dipole is placed in an external electric field. So electric field direction is shown here. Now the two charges plus q and minus q are separated by a distance d here. Theta is the angle between the electric field and the dipole moment vector. Now there is a force on each charge plus q and minus q due to the presence of the electric field, and we know that this force is given by F is equal to QE. So a QE force will be acting on plus q charge in the direction of the electric field, and the same F is equal to QE. QE force will be acting in the direction opposite to that of the electric field on minus q. Now, at the two ends of the dipole, two equal and opposite forces will be acting due to the electric field. We know that two equal and opposite forces acting at two different points on an object will constitute a couple of forces. Now, so these two forces will produce a turning effect. These two forces acting at two different points will produce a torque, and torque due to this couple of forces is equal to product of any one of the force into arm of the couple. What is arm of the couple? Is the perpendicular distance between the two forces. That is arm of the couple. What is the perpendicular distance between the two forces? If d is the length of the dipole, then arm of the dipole is d sine theta. The perpendicular distance between the two forces will be d sine theta. So torque is equal to QE into d sine theta. Now Q into d, we know that charge into distance is dipole moment. So torque is equal to PE sine theta. That is, tau is equal to P cross E. Torque experienced by a dipole placed in an electric field is equal to tau is equal to P cross E. So an electric dipole placed in an external electric field experiences a torque. Now let us discuss about some importance of electric dipoles. We know that all materials are made up of extremely small particles called molecules, and of course these molecules are made up of again by atoms, smaller particles called atoms. Now if you take molecules of most of the substances, so there are charges in the molecules. There are positive charges and there are negative charges. Now in most cases, the negative charge center and positive charge center of a molecule coincide. The negative charge center and the positive charge center, what are they? Then we know that negative charges are distributed and positive charges are not at one point. It is also distributed within the nucleus. Now, if you consider a molecule as a whole, we can consider a point where the entire charge is assumed to be concentrated. That point we call negative charge center. Similarly, a point where entire positive charge is assumed to be concentrated, we can call positive charge center. Generally, negative charge center and positive charge center, they coincide. Therefore, this dipole is electrically neutral, and since these two charge centers coincide, the net dipole moment of the molecule will be zero. The molecule will not act as a dipole, neutral molecule, as shown in the figure. The yellow mark indicates positive charge center and the blue mark indicates negative charge center. In all the molecules, they coincide. Now, when an object or a material is placed in an electric field, in an external electric field, in presence of this electric field, these negative charge center and positive charge center both will experience a force in the opposite directions. Positive charge centers will experience a force in the direction of the field, and negative charge centers will experience a force opposite to the direction of the electric field. Due to this force, equal and opposite forces, these negative charge center and positive charge center will be separated slightly. Now this is equivalent to that of a dipole, an electric dipole. So lot of molecular electric dipoles will be produced in the body due to the presence of an external electric field, as shown in the figure. So we can say the material is polarized due to the presence of the electric field. So this process this phenomenon is called polarization of a material. Okay. But in some cases, even without the presence of an external electric field, the molecules of some substances will have electric dipole moment. They act as electric dipoles. Such molecules we call polar molecules. For example, water is a polar molecule, hydrogen chloride is a polar molecule, acetic acid. These are some examples for polar substances. What is the reason for this polar nature of these substances? One example we will discuss. Consider a water molecule. So water molecule is formed by one oxygen atom and two hydrogen atoms, and hydrogen and oxygen shares two electrons, and on the same way the another hydrogen and oxygen will share a pair of electrons. And here hydrogen is electropositive and oxygen is highly electronegative element. Due to the high electronegativity of oxygen, these paired electrons will be slightly pulled towards the side of the oxygen. Therefore, the part of oxygen will be slightly negative and part of hydrogen will be slightly positive, since the paired electrons are pulled slightly towards the side of oxygen due to its high electronegativity. Paired electrons will be slightly shifted from the equilibrium position. Therefore, this molecule will have a positive pole and a negative pole, and it will act as a polar molecule. Same case of hydrogen chloride. Hydrogen and chlorine. Chlorine is highly electronegative. Hydrogen is electropositive. So chlorine will attract the shared electrons towards the side of the chlorine. So it will be slightly shifted from the equilibrium position, and therefore hydrogen will acquire a positive and chlorine will acquire a negative charge. So it will act as a polar molecule. Okay. So lot of materials are there that they exhibit polar nature without external electric field. For example, hydrogen chloride, water, acetic acid, ammonia is another ammonia gas. They are some examples of polar molecules. Now let us discuss some problems related to electric dipoles. Two charges plus 10 microcoulomb and minus 10 microcoulomb are placed 3 millimeters apart from each other in free space. What is the dipole moment of the system? We know that dipole moment is charge into distance between them. P is equal to Q into A. That is 10 into 10 to the power of minus 6 into 3 into 10 to the power of minus 3. That is 3 into 10 to the power of minus 8 coulomb meter. Coulomb meter is the unit of dipole moment. Next problem. A uniform electric field of 2 into 10 to the power of 5 Newton per coulomb is set up in free space. A sample of hydrogen chloride gas is placed inside this field. What is the maximum torque experienced by the hydrogen chloride molecules? Given the dipole moment of the HCl molecules is 3.4 into 10 to the power of minus 30 coulomb meter. We know that torque experienced by a dipole placed in an electric field, tau is equal to Pe sin theta, where theta is the angle between the electric field and the dipole moment vector. Now, torque will be maximum when sin theta is 1, that is when theta is 90 degrees. Now, torque tau is equal to 3.4 into 10 to the power of minus 30 into 2 into 10 to the power of 5. That is 6.8 into 10 to the power of minus 25 Newton meter. Here one problem is given for practice. I recommend you to solve this problem yourself and comment the answer in the comment section of this video. And thanks for watching this video. I hope this helps you to prepare for your exams and for other competitive examinations. If you like this video, please subscribe and share this video. Thank you. Thanks for watching.